Welcome to this presentation. My name is Mark Scythian. The date today is June 13th, 2025. So this presentation is going to focus on a concept known as the mechanical battery. So we will harness mechanical moment of inertia from a spinning disk and transfer this energy to an electric generator. But however, this is no ordinary rotating disk. So we have this 4,000 pound, 4-inch thick solid steel or water filled disc rotating on spindle bearings with a 6-foot diameter. So this is dynamically balanced and then mounted to a set of bearings mounted into above the ground carefully. So there'll be a lot of energy, and then connected to a starter generator. So this starter generator would only deliver 50 horsepower mechanical brake horsepower, gear reduced, so that would be a very small gear rotating a very large gear. So the practicality is such that you could turn it on, and this 4,000 pound disc flywheel would start to slowly rotate until it reaches 3,500 RPM. So we'd like to keep the outer radius at a tangential velocity of about 1,100 feet per second, because this is about where airflow shock waves would develop at 1,100 feet per second. At room temperature air, that's the speed of sound. So we'll take this large disc and rotate it just to the speed of sound, just below it. So if we do the equations on figuring out the rotational kinetic energy at 3,500 RPM, this becomes around 58.33 revolutions per second. So we had 2 pi radians per 1 revolution. So we can calculate 366.5 radians per second is 3,500 RPM. And then the rotational kinetic energy is 1/2 times I, moment of inertia, times the angular velocity squared. But we have to make sure it is the we have to make sure this is the moment of inertia of a solid disk, because there's many different moment of inertias, like for a hollow sphere or a solid sphere or a hollow disk or a solid disk or any other shape that could rotate. So they all have different moments of inertia, but for a solid disk, that is the 1/2 m times r squared formula. So we can then take 1/2 times the mass of the disk in kilograms, dividing the pounds weight into 2.2, and then taking the radius, which is 3 feet, 6 feet diameter. So 3 feet radius, dividing that by 3.28, so 0.91 meters radius. So we square that value. So this is our moment of inertia, 752.8 kilogram square meters, and then we enter that I value and multiply it times this 366.5 squared times 0.5. So then we calculate a rotational kinetic energy of this disk right around 50.56 megawatts of mechanical power. So again, we cannot create or destroy energy. We can only change it in form. So that accumulated moment rotational kinetic energy is accumulated from just 50 brake horsepower from the motor. So that would be 50 times 746, and then we divide that into 0.85. So it's something around 50,000 watts of electrical power to get 37,300 watts of mechanical power. And then we have about a 10% loss in friction at the bearings here. So we can estimate about 45.5 megawatts of usable mechanical power is available at the disc, just because of the moment of inertia so high, so large on it, 4,000 pounds disc rotating at 3,500 RPM. So we can use this to assist our power recovery and then use this for some sort of an alternative power application. So again, we will also take away another 10% from the motor's RPM and torque input into the disc through gear reduction. So it's really 33,570 watts. So if we were to divide this and figure out the charging time to charge the rotating disc or the mechanical battery, it would take about 23 minutes of running that motor at 50,000 watts. So it would be about 2.5 kilowatts of power. 50,000 divided by 1,005, and then it's a little less than 2.5, maybe 2.3, 2.2 at 23 minutes. So not too bad. And then if we just get an idea of the percentage draw from the standing energy, it's obvious that, if we were to return that power back to the motor, it'd just be a really minuscule amount of percentage. But this is over a duration. So the goal is to put some energy in and see how much we can recover back out through the heavy disc rotating. So again, we could supplement some of that power loss with a solar panel and an auxiliary DC motor to just give it a little push more. And of course, that would have to be a limited slip clutch. So the rotor does not drive the auxiliary DC motor, but instead, based on getting a step-up gearing, we could have the brake clutch engage some of that motor just to give it a little push. But we'd have to be very careful because there's a lot of energy in this disc. There should be a very maintained safe distance, because if this disc fell apart, it would just be horrible. It would be equivalent to a 50 megawatt power plant coming apart. So we're taking advantage of the weight and the RPM. So what we have to do is just spin this up, charge it over 23 minutes, and then disengage the starter and see how long this disc would take to just slow down under the friction. So we have to find the average coefficient of kinetic friction of bearings. So that's the mu sub k, that is the coefficient of friction of bearings, and it's all the way from like 0.004 to 0.15 or something. So I got the average value of all bearings, 0.2. So if we take the force weight, the weight of the disc times the coefficient of kinetic friction, 0.2, we'll get the force friction incurred. So we could take 4,000 pounds and make it newtons, 4.45 newtons to a pound of force, and then multiply this times 0.2, so we get 3,560 newtons. We can divide this into 4.45, so we get 800 pounds of force And if we were just to take the 45.5 megawatts here and divide it into 746, then we can get the brake horsepower times 550. So that's the number of foot-pounds per second to horsepower. We calculate this large 33,545,576.4 foot-pounds per second value. And we literally could just divide this into a draw or friction deficit, a friction draw no load as the quotient over 800. So we would have enough momentum to where the nonlinear reduction in RPM would be irrelevant. So it's relatively going to stay linear because of the weight. So it's more or less close to just a linear function. So we could divide that into 800. So this will take about 41,932 seconds, 11 hours to stop rotating under no load. Because picture it, that's 2-ton disc, 6 foot in diameter, rotating at 58.33 revolutions per second, 3,500 RPM. That's pretty, I mean, if it wasn't dynamically balanced, it would be extremely dangerous. But let's say all that has been worked on and it's incrementally increasing RPM. You would have to wait almost a half a day to see it stop just from the friction. So now it's functioning something like a mechanical battery. So this is not a new concept, momentum drives. But it should be considered into the alternative power or the green energy applications. And that would get really expensive to just have a really thick steel disc. But it could be a hollow steel disc then filled with water and then bled. You might have to make it a little thicker, but there's considerably more density in steel compared to water, but you could get the cost down and make the construction simple if water could take the place of solid steel, thicker disc, and then bled out from air, and then it would just be solid without any sloshing of the water. It would just be a solid hydraulic type of a disc, incompressible inside the container. So that could be a hollow disc welded together with steel circular plates and then circular cutouts then welded across. You could do that, right? But anyway, or it could be bolted and then welded across for simplicity. So if we had 60,000 watts then tapped out of this disc to drive an AC generator with 85% efficiency, we could get 51,000 watts of AC power for 991 seconds, which is about 3 times 15, 16 minutes. But chances are that's like all the power in a household when you would probably be using just about 10% of it at any given time, maybe 20. So if you were just using 10% of it, this rotor could power that house for 2.76 hours. And if it was all of it, about 16.5 minutes. So the idea is that, of course, it's not significant as per source of power, but what is interesting is just to keep it running, it would require an input power of at least 800 foot-pounds per second to overcome the friction. So if we had an alternate motor on the other side that could use a limited slip gear step up brake clutch, so whatever power you're trying to draw into the motor, it would be a very large gear on a small one. It would be just enough to overcome friction. And what does that translate to practically in horsepower? You'd have to put a little solar powered motor on that disc. And just it would only need 1.45 horsepower to keep it running under no load at constant speed. So then again, that is what you're getting assistance in. But still, it's going to conserve energy. You can't get energy from nothing. So if you tap 60,000 watts of power to that rotor, you'd have to simply just divide the 50.56 megawatts into 60 kilowatts, and that would give you the runtime. So if we did that right now, that would translate to 50.56 E6 divided into 60 E3. So you get 842 seconds. And that would give us about 14 minutes of runtime. So it's not a whole lot of power, but if we improved on many of these drives with minimal solar powered motor support to overcome the friction, we would definitely have a substantial reduction in the consumption of the power. So this is kind of how large combustion engine flywheels would maintain a lot higher efficiencies for not the thermal efficiency, but the mechanical efficiency, by putting a large harmonic balancer that is having significant weight to take advantage of the moment of inertia and the additional rotational kinetic energy. So again, it is not a whole lot because we can't create or destroy energy, but we would substantially decrease the amount of power we need to consume with a momentum, i.e. moment of inertia assistance. And one more application that's probably the most practical is to just take this disc and run some turbine blades across the edge. We'd have to put substantially more turbine blades. Auto shape is kicking in. We would have a bunch of turbine blades going around, and then we could frame this in a little collector here. Then we could pass just a little bit of steam power through these turbine blades. And we would not need a lot, because if we vaporize 1 pound mass of water per 1 second, including thermal transfer losses, let's say natural gas heating water, it would take about 300 to be 289.36. Divided into 0.8, so about 360. 362 BTUs per second. If we are converting 1 pound of water to steam in 1 second, and that steam is at 316.25 degrees Fahrenheit, we can only use 20% of it to actually drive a turbine. So this would become 289.36 times 1056. And then that yields 1184.2 BTUs per pound. So 1184.2, but this time it goes kinetic, so it's per second now. It would be 1.25 million watts of steam times 20%. So we would have 250,103, and all we need is about one. We don't even need that much. We need like 10% of that. Let's say 25,000 watts. So that's only 0.1 pounds of water vaporized to steam, 316.25 degrees Fahrenheit in 1 second. So all we need out of the natural gas is 36.2 BTUs per second, and every pound of natural gas has 24,800 BTUs. So that would only cost, we'll just say an hour to run it. It would only cost half a pound of natural gas per hour to run this giant turbine, a steam turbine assisted momentum drive. So this could be called a mechanical we could call this a mechanical battery, but we call it steam. Call it the Rankine-Cycle. Mechanical battery. Or just RCMB. And this is the green technology. And it does not violate any of the 4 laws of thermodynamics. It's within the mechanical and aerospace engineering standards under the physics realms. And so this is not a new concept. Actually, there's a few companies actually building these. But we need to probably look to keeping the alternative power simple and grounded to the laws of classical physics so that it can be taught, and almost anybody could build these if they have about 10 people construction crew. And these would take the nation by storm, and then we don't have to toss out solar panels. We could use them for a bit of drive assistance. But if we built one of these units with a steam boiler on board, you could pass the steam from the boiler at very low rates just to keep this disk running. And the steam would not be wasted. It would go back into a collector and then a condenser, and then come back into the boiler as hotter condensed water and restart over. But the temperature would have to be kept right there about 300 degrees. Anything hotter, this system would fall apart pretty quickly, but you could have this unit going and it'd be very, 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 very tiny amount of fuel consumption to run it. So if you improved on this, you could decrease the cost of electricity after the equipment is paid off by as much as 50 to 80%. If we include all the other expenses, taxes, fees, overhead, licensing, etc., you at least drop the cost of electricity by 50% at the very minimum, and also the emissions would drop down to almost nothing, because you could also incorporate in natural gas furnaces, boilers. You could also incorporate catalytic reheating, just like on cars. So carbon monoxide could be converted to carbon dioxide. which is plant food, by the way. Carbon dioxide plus sunlight equals photosynthesis. And if you keep catalytically reheating, you can reduce all the natural gas into carbon dioxide and water at very, 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 very tiny trace amounts of oxides of nitrogen and sulfur, which would be almost irrelevant. So now you have a real green technology, and the concept is easy to understand. It's not out in the electromagnetic field. It's not purposely made complex, because that's what many engineers and business owners like to do, is to make it intentionally complex. So you literally have to finish your engineering degree at the university before you can even comprehend what's going on, let alone maybe work 5 or 10 years as a technician to figure it out. But this is not hard to figure out. This is something you could host a class and orientate everybody how this basic technology works. It's all because of moment of inertia. And people would really know how to get together quickly and build these units. This would create a lot of jobs, because people, if they're willing to work, they can build these. And they're based on the concept of moment of inertia. So if you have a bench grinder, you notice the moment of inertia is very good on it, right? It's kind of a heavy disc for the size. And you shut off the bench grinder, and again, it's connected to a de-energized AC motor, which has got dipoles that are also fighting against the rotation. But you notice how long it takes to slow down. That's because that's intentionally made. The bench grinder is a good example. It's intentionally made as high moment of inertia. So, it's got a bit more torque and rotational kinetic energy to grind apart whatever you're working on. So you're really supposed to use the light pressure and let the grinder take the load, right? So you don't overheat, you don't kind of dull or ruin the aluminum oxide disc, right? But this additional power, rotational kinetic energy, is harnessed by increasing the mass and the radius, and the RPM. So we have pretty big diameter, and we have pretty good weight, and we have a pretty good RPM. So we're going to get, at the 3500 RPM mark, about 50.6 megawatts of mechanical power from that disk. And so that would function like a mechanical battery. And again, on the left side here, you could put an auxiliary drive motor, which is again a large gear going to a small gear. So even putting in a little bit of power, like 1.45 horsepower, is going to transmit into this disc and overcome the friction at the bearing. So this thing would be running off of a solar powered auxiliary drive, and then it could be used to charge a set of batteries all day, including capacitance, so that it could power systems from an inverter DC to AC during the nighttime hours. So that would be a purely green, no emissions technology. But you also could make something really large and have it become also a turbine disc at the outer reaches, and have it supplementally powered on a little bit of steam power, which burns very little natural gas, including catalytic reheating. But if you were to go completely combustionless, then you could supplement this 800 foot-pounds or 800 foot-pounds per second or 1.45 horsepower by solar powered DC electric motor that's step-up geared rather than step-down like it is here. We would have a smaller gear driving a large one. This one's just the opposite. We would have a large gear driving a small one. So we already have this large amount of momentum and torque. We just need to give it a little push. This motor, this would be the motor right here, and this would be connected here. So again, it's all very feasible, and something like scaled down could be built where you would somehow get a little 6-inch diameter disc that weighs 20 pounds. You'd have to look for some really heavy metal and try to weight it down and put it on a bearing, and you could make an LED circuit from it and do things like add a supplemental motor, and the scaling factor would be relatively linear if you scaled it up. So more of these have to be on the market, I think. However, the technology's already been figured out. We just have people who consider protecting their jobs more important than making breakthroughs, because breakthroughs tend to take away jobs and make things easy, and you don't need a lot of people trying to solve any problems anymore. So that's the conundrum. So at the very least, people probably should get busy and build their own mechanical battery. So please leave comments in the comment section and let me know if any of you have started on a project similar to this. More emphasis on power recovery systems will start to populate my YouTube library in the future. So thank you for watching this presentation, and have a great day.